Welcome to this lesson on AP Statistics, Topic 3.8. Today, we are exploring the critical concepts of Type 1 and Type 2 errors, along with the power of a statistical test. By the end of this session, you will be able to identify and interpret Type 1 and Type 2 errors, calculate the probability of these errors, and understand the factors that affect the power of a test. This is a fundamental skill for the AP exam, specifically Skill 2.D and 4.D, which focus on interpreting results and identifying potential flaws in conclusions. In every hypothesis test, we start with a null hypothesis, which we call H0, and an alternative hypothesis, H sub A. We collect data and make a decision. Either we reject the null hypothesis or we fail to reject it. However, because we are using samples to make inferences about populations, there is always a chance we make the wrong call. To understand these errors, let's look at the 4 possible outcomes of a hypothesis test. 2 outcomes are correct, and 2 are errors. Let's fill this in. If the null hypothesis is actually true in reality, but our data is so extreme that we decide to reject it, we've made a mistake. This is a Type 1 error. Think of it as a false positive. We claim to find an effect that doesn't actually exist. Now, what if the alternative hypothesis is actually true, meaning there really is an effect, but our data isn't strong enough to prove it? This is a Type 2 error. Think of it as a false negative. We missed the truth. If we reject the null when the alternative is true, we've made a correct decision. The probability of doing this is called the power of the test. And finally, if we fail to reject a true null hypothesis, we've also made a correct decision. Understanding this grid is the first step toward mastering Topic 3.8. Our goal today is to learn how to identify these errors in real-world scenarios. Let's formalize the definition of a Type 1 error, so you can spot it in any AP statistics problem. A Type 1 error occurs when there is convincing statistical evidence that the alternative hypothesis is true, usually because we got a very small p-value. But in reality, the null hypothesis is actually true. Imagine a pharmaceutical company testing a new medication. Our null hypothesis, H0, is that the drug is not effective. The alternative, H sub A, is that the drug is effective. If the researchers conduct a study and find a very small p-value, they will reject the null hypothesis and conclude the drug works. But what if the drug actually does nothing, and they just happen to get a lucky sample? In this context, a Type 1 error means concluding the drug is effective when it actually is not. In this case, the Type 1 error means patients might be taking a medicine that doesn't help them, and the company is wasting resources. The probability of making this specific mistake is something we actually control before we even collect data. It is exactly equal to our significance level alpha. If you set alpha to 0.05, you are essentially saying, I am willing to accept a 5% chance of rejecting a true null hypothesis. If you want to be more careful and avoid this error, you would lower your alpha to 0.01. Now, let's look at the flip side, the Type 2 error. A Type 2 error occurs when we do not find convincing statistical evidence that the alternative hypothesis is true, meaning our p-value is not small enough. But in reality, the alternative hypothesis is the truth. Let's go back to our pharmaceutical example. The null hypothesis is that the drug is not effective, while the alternative hypothesis is that the drug is effective. If the researchers get a large p-value, say 0.24, they will fail to reject the null. They'll conclude there isn't enough evidence to say the drug works. But what if the drug actually is a life-saving breakthrough, and their sample just happened to have a few outliers that masked the drug's effectiveness? In this context, the Type 2 error means concluding there is no evidence the drug works when it actually does. The consequence here is different. Instead of giving people a useless drug, we are failing to provide a beneficial drug to the public. We represent the probability of a Type 2 error with the Greek letter beta. Unlike alpha, we don't just set beta at the start of a test, but it is deeply related to the concept of power. Power is defined as 1 minus beta. Power is the probability that we correctly reject a false null hypothesis. If the drug works, power is the probability our test is strong enough to prove it. If we have a high Type 2 error rate, we have a low power test. To truly master these concepts for the AP exam, you must be able to describe the consequences of these errors in context. Let's work through a detailed example involving safety. Imagine a company that manufactures smoke detectors. They test each unit before shipping. Our null hypothesis, H0, is that there is no smoke, meaning the alarm should stay silent. The alternative, H sub A, is that there is smoke, and the alarm should sound. Let's identify the type 1 error first. Remember, a type 1 error is rejecting a true null. In this case, the type 1 error is that the alarm sounds when there is no smoke. What is the consequence of this? It's a false alarm. This causes annoyance, potential panic, and could lead to people ignoring the alarm in the future or removing the batteries. It's a nuisance, but is it the worst possible outcome? Now, let's look at the type 2 error. This is failing to reject a false null. The type 2 error is that the alarm stays silent when there is actually smoke. Think about the consequence here. The detector fails to warn residents of a fire. This is much more serious. It could lead to property damage, injury, or loss of life. So, comparing the two, type 1 is an annoyance, while type 2 is a major danger. In this specific case, the consequence of a type 2 error is significantly more severe than a type 1 error. Because of this, the manufacturer would want a test with very high power to ensure that if there is smoke, the alarm will definitely go off. Take a moment to think. If you were the engineer, would you choose a high alpha or a low alpha for this test? We'll answer that soon when we talk about the relationship between these two errors. It is a common mistake to think we can just make both error probabilities 0. Unfortunately, there is a natural trade-off between type 1 and type 2 errors. Think of alpha and beta on a seesaw. If you want to decrease the probability of a type 1 error, you lower your significance level alpha. But as alpha goes down, the bar for evidence becomes much higher. Because you are being so strict about rejecting the null, you are more likely to miss a true effect. When alpha decreases, beta, the probability of a type 2 error, increases. And since power is 1 minus beta, when beta goes up, power goes down. Now, imagine the smoke detector example again. We decided the type 2 error, the alarm staying silent during a fire, was more dangerous. To minimize that risk, we want a very small beta. To get a small beta, we have to increase alpha. By making the alarm more sensitive, increasing the significance level, we ensure it sounds even for small amounts of smoke. This increases the chance of a false alarm, a type 1 error, but it protects us from the much worse type 2 error. In summary, decreasing alpha leads to an increased beta and decreased power. Increasing alpha leads to a decreased beta and increased power. When you are asked on the exam to choose a significance level, look at the consequences. If a false positive is worse, use a small alpha like 0.01. If a false negative is worse, use a larger alpha like 0.10 to boost your power. Now that we understand the trade-off between alpha and beta, let's focus specifically on power. Remember, power is the probability of making the right call when an effect actually exists. Power is our friend. We want it to be high, ideally 0.80 or higher. But if we don't want to just keep increasing alpha and causing more type 1 errors, how else can we increase power? The most common way to increase power is to increase the sample size. When n increases, the standard error decreases. This makes our sampling distribution narrower and more precise. A more precise test is much better at detecting a difference, which directly increases the power and decreases the probability of a type 2 error. As we just discussed, increasing alpha makes it easier to reject the null. This naturally increases power, though it comes at the cost of more type 1 errors. This is called the effect size. Think about it this way. If you are looking for a needle in a haystack, it's hard to find. But if you are looking for a bowling ball in a haystack, it's easy. If the true population parameter is very far away from the hypothesized null value, your test is much more likely to detect that difference. Therefore, a larger effect size leads to higher power. If the data itself is less noisy, meaning the population has a smaller standard deviation, it is easier to see the signal. Reducing variability in your measurement process increases power. In summary, to boost your power, get more data, accept a higher alpha, look for bigger differences, or reduce noise. Let's put all these concepts together with a comprehensive worked example. This is exactly the type of question you might see on an AP free response section. A city's water department tests for lead levels. The safety limit is 15 parts per billion. If the average lead level is above 15, the water is unsafe and must be treated immediately. Our null hypothesis is that mu equals 15, meaning the water is safe enough. The alternative is that mu is greater than 15, meaning the water is unsafe. First, let's identify the type 1 error and its consequence. A type 1 error occurs when we conclude the water is unsafe, rejecting the null when it is actually safe. What would happen? The city spends thousands of dollars on unnecessary treatment, chemicals, and causes public panic for no reason. Now, identify the type 2 error and its consequence. A type 2 error is concluding the water is safe, failing to reject the null, when it is actually unsafe. What would happen here? Citizens are exposed to dangerous levels of lead, leading to long-term health issues, especially in children. Which error is more serious? In this context, most would agree the type 2 error is more serious because it involves a public health crisis. How should the department set their significance level alpha? Since the type 2 error is more dangerous, the department wants to minimize the probability of that error, which is minimizing beta. As we learned from our seesaw analogy, to make beta small, we should make alpha larger. Instead of using a strict 0.01, they might choose a 0.10 level. This increases the power of the test, ensuring that if lead is present, they are very likely to detect it and take action. Take a moment to process that. Increasing the chance of a false alarm is a calculated risk to prevent a missed catastrophe. To help you visualize why these factors affect power, let's look at the actual distributions involved in a hypothesis test. This visual approach helps bridge the gap between memorizing the rules and understanding the logic. The distribution on the left represents what we expect to see if the null hypothesis is true. The distribution on the right represents the reality if the alternative hypothesis is true. The area under the null curve beyond our critical value is alpha, our type 1 error. If we get a sample mean in this region, we reject the null, even though the null was true. Now look at the alternative curve. If the alternative is true, but our sample mean falls to the left of that same vertical line, we fail to reject the null. This area is beta, the probability of a type 2 error. The remaining area under the alternative curve, the success zone where we correctly reject the null, is our power. Notice what happens to that power area as the true mean moves further away from the null mean. The curves separate, beta shrinks, and the power area grows. This illustrates why a larger effect size makes a test more powerful. Now, imagine we increase our sample size. This makes the standard error smaller, so both curves become thinner and taller. Look at the overlap, it shrinks. As the curves get narrower, the area for beta gets much smaller, and the power increases. This is why more data is almost always the best way to improve a study's reliability. Visualizing these overlapping curves is a powerful mental model. If you can move these curves in your mind, you can answer any conceptual question about power on the exam. Let's practice a few more scenarios to ensure you can identify these errors in various fields. This will help you build the statistical intuition needed for high-stakes testing. In a criminal trial, our hypotheses are H0, the defendant is innocent. H sub A, the defendant is guilty. A type 1 error is rejecting the null when it is true. In this case, it means convicting an innocent person. The consequence is a gross injustice and a loss of freedom for someone who did nothing wrong. A type 2 error is failing to reject the null when the alternative is true. This means a guilty person is acquitted and goes free. The consequence is that a criminal is back on the streets, potentially posing a risk to society. The United States legal system is built on the principle of innocent until proven guilty, which implies that a type 1 error, convicting the innocent, is considered much worse. This is why the significance level in a courtroom, often called beyond a reasonable doubt, is set extremely high. We would rather let several guilty people go free than convict one innocent person. A company is testing if a new website layout increases the proportion of users who click an ad. H0, click rate is the same, P equals 0.10. H sub A, click rate is higher, P is greater than 0.10. A type 1 error occurs if the company concludes the new layout is better when it actually isn't. The consequence is, they waste time and money implementing a change that doesn't actually help their revenue. A type 2 error occurs if the company concludes the new layout is not better when it actually is. The consequence is they miss out on a significant opportunity to increase their profits. In business, the worst error often depends on the cost of the change. If the new layout is expensive to build, they'll want a very small alpha to avoid a type 1 error. If the layout is cheap to implement, they might use a larger alpha to ensure they don't miss any potential gains. We've covered a lot of theory, so let's consolidate this with some calculation-based logic. While the AP exam often focuses on interpretation, you must understand how the numbers relate. Understand the mathematical relationships between alpha, beta, and power. Remember our two key formulas. 1. Probability of type 1 error equals alpha. And 2. Power equals 1 minus probability of type 2 error, which we call beta. Suppose a researcher is conducting a medical trial and sets the significance level, alpha, at 0.05. In the design phase of the experiment, a computer simulation determines that the power of the test against a specific alternative is 0.80. What is the probability of a type 1 error? This is the easy part. The probability of a type 1 error is simply alpha. So, it is 0.05 or 5%. What is the probability of a type 2 error? Using our second formula, we rearrange it. Beta equals 1 minus power. Beta equals 1 minus 0.80, which is 0.20. So, there is a 20% chance the researcher will fail to detect the medical effect even if it exists. If the researcher wants to reduce the type 2 error rate to 10%, what should they do? To make beta smaller, they need to increase the power to 0.90. As we discussed, they can do this by 1. Increasing the sample size, or 2. Increasing the significance level, alpha. If they choose to increase alpha, say to 0.10, they successfully reduce the risk of a misdiscovery, but they simultaneously double their risk of a false discovery. Let's summarize these proportions. If alpha is 0.05, type 1 risk is 5%. If power is 0.80, type 2 risk is 20%. This mathematical balance is the heart of experimental design. Researchers must decide which risk they are more comfortable with before they ever start collecting data. To help you prepare for the AP exam, let's look at how these topics are typically phrased in multiple-choice questions. Being able to decode the wording is half the battle. Consider this sample question. A test of hypotheses was performed with a significance level of alpha equals 0.05. If the null hypothesis is true, which of the following is the probability that a type 1 error will be committed? Here are our options. This is a direct test of the definition. By definition, the probability of a type 1 error is alpha. The answer is A. Don't let the other distractors confuse you. If the null is true, the only error we can make is type 1, and its probability is alpha. Now let's look at sample question 2. Which of the following would result in an increase in the power of a hypothesis test? We have 3 Roman numeral statements. 1. Increasing the sample size. 2. Increasing the significance level. 3. Increasing the standard deviation of the population. Let's check each one. 1. Increasing sample size? Yes, this reduces standard error and increases power. 2. Increasing significance level? Yes, this makes it easier to reject the null, increasing power. 3. Increasing standard deviation? No. More variability makes the data noisier, making it harder to detect an effect, which decreases power. The correct answer is C, statements 1 and 2 only. Here is an exam tip. When you see power on the exam, think ability to find the truth. Anything that makes the data clearer, like more n or less sigma, or the decision easier, like a higher alpha or a larger effect size, will increase power. We have covered a lot of ground today on the complexities of statistical decision-making. Let's do one final recap to ensure you are ready for topic 3.8. First, let's look at our summary table. A type 1 error is rejecting the null when it is actually true, represented by alpha, often called a false positive. A type 2 error is failing to reject the null when it is false, represented by beta, or a false negative. We have successfully identified these errors in context, calculated probabilities using alpha and power, and explored factors like sample size and significance level that affect power. Remember the core takeaways. Type 1 is a false alarm, while type 2 is a missed opportunity. There is always a trade-off between the two. You cannot decrease one without increasing the other unless you change the sample size or the variability of your data. When you face an AP problem, follow this checklist. Identify your hypotheses, define the error in context, describe the real-world consequence, and check how changing n or alpha shifts the risks. In your future studies, you'll see that power isn't just a term for a test, it's a requirement for ethical research. Conducting a study with low power is often seen as a waste of resources because you are unlikely to find the truth even if it is there. Statistical significance is not just about the math, it's about the consequences of being wrong. Take some time to practice the practice problems in your textbook using these visual models. Focus on writing out your explanations in full sentences as the AP graders look for clear communication of these concepts. Good luck with your studies, and I'll see you in the next topic.